Welcome to today's AI for Manufacturing webinar. My name is Li-Hui Wang of KTH Royal Institute of Technology. I'm the curator and the moderator of this webinar series. Together with UNIDO, ITU launched the AI for Manufacturing webinar in September of this year to provide a forum for leading research work, policies, and best practices in different sectors, focusing on how AI technology can be used to benefit manufacturing. The theme of today's keynote is about industrial AI for trust worry-free manufacturing. We are fortunate to have Professor Jay Lee with us today. Professor Lee is an Ohio eminent scholar, L.W. Scott Author Chair, and University Distinguished Professor at the University of Cincinnati, and founding director of National Science Foundation's Industry University Cooperative Research Center, IUCRC, on Intelligent Maintenance Systems, IMS, in partnership with over 100 global company members. IMS was selected as the most economically impactful IUCRC in the NSF Economic Impact Study Report in 2012. He is also the founding director of Industrial AI Center. He mentored his students and developed a number of startup companies, including Predictive through NSF ICOP in 2013. He was on leave from University of Cincinnati to serve as the vice chairman and board member for Foxconn Technology Group during 2019 to 2021 to lead the development of a Foxconn Wisconsin Science Park in Mount Pleasant. In addition, he advised the Foxconn business unit to successfully receive the 5 WEF Lighthouse Factory Award since 2019. He is a member of Global Future Council on Advanced Manufacturing and Production of the World Economic Council, a member of the board of governors of the Manufacturing Executive Leadership Council of a National Association of Manufacturers, board of trustees of MT Connect, as well as a senior advisor to McKinsey. Previously, he served as the director of product development and manufacturing at United Technologies Research Center, as well as a program director for a number of programs at NSF. He was elected one of the 30 visionaries in smart manufacturing by SME in January 2016, and one of the 20 most influential professors in smart manufacturing in June 2020. He also received 2022 SME Ellie Whitney Productivity Award and the 2022 SME NAMRI SMU Research Implementation Award. Without further ado, please join me in welcoming Professor Jay Lee. The platform is yours.
Thank you, Professor Wang, and for the introduction. Am I sound okay?
Yes.
Okay. So can everyone see my screen? Yeah. Okay, so today I'm very pleased to have this opportunity to share with the panel and the audience about industrial AI for worry-free industrial system. Of course, manufacturing is one big industrial system. Certainly, when I name the worry-free, mean in the manufacturing industry, right, we work very hard every day. But the problem is you always worry about many things like quality, efficiency, uptime, OEE, throughputs, delivery, many things, even worker safety as well, in emission carbon reduction. So there are many things we have to worry. But of course, one way to make sure we don't worry is that you have to take the data, make it transparent. But beyond that, we have to make predictive. Before things happen, we know something going to happen. So you can prevent from happening, right? So eventually you can achieve the goal without worry. So let's do this. How we make it happen? So I will basically go over, first give introduction, also look the trends of a IoT, and all the systems are connected because we have to manage a large amount of data. So the one thing people will think, oh, I need to connect everything. Do we really need to connect everything? Or they are connectable, but we only connect to the right things, right? So only connect to the right things, but most of the things are connectable. So then how we differentiate? But by doing that, of individual machines have a lot of uncertainties, variations, and data quality. They may be made by different vendors, different user, different generation of the production, and those different materials. So that not everything is the same. Now, how we categorize these similarities? Of course, when you have a data-centric predictive method, now how we predict the system, right? Now, I give some example. First, before we start, I'll give just one slide. And we start a center about 2000 to build this called the vision of IMS, Intelligent Maintenance System. That was based on year 2000 when I worked at NSF and during 1991 to 98. And we always thought that one day things were connected. But the problem is in year 2000, phone is not connected to internet. Most of us could not connect to internet using phone, right? You cannot browse. So the guess will be, what happened if things could be connected? Then what will you do at that time? So we set a threshold, say, well, we're going to assume when system connected, these are things will happen. First of all, data will be flying out, right? You can connect the data. Now, how you analyze data, like in the doctor take the blood from human, we can understand your problem. Now, machine blood is data. Can we understand the same thing about the health? If we can, then we can predict almost just in time what's going to happen. And we can close loop, feedback to design, make system better, right? Of course, eventually you have a zero downtime. That was a vision year 2000. Over years, we work with over 100 companies globally, and between Cincinnati, University of Michigan, Ann Arbor, and UT Austin, I think we have done a quite different type of scale in terms of how we demonstrate this capability and with value in return. So certainly over years, you can tell that, and we start from zero downtime back in 2000. And worry-free system we launched in 2014 to help a lot of companies start focusing on 2019. And we helped Foxconn get the first lighthouse with a worry-free system, eventually propagate to many different systems. So this has been over the several spin-offs, and students continue developing, right? That's just a background. Now, trend of IoT and also uncertainty, variation, and data quality. When the systems are connected, now obviously one thing will be after the next 10 years, we see lots of industrial system will be connected. So therefore, data become a centric, no longer just option. So you will use data as a centric way to do things. So data-centric things will happen. But the problem is, the question will be, but are we ready to manage in such a data-centric system? It's not just how many servers, how many the HPC you have. No, it's not about that. Do you have a good domain knowledge to managing these disciplines that using this data? I go 3D, data, domain, discipline. So therefore, when those growth will continue, then obviously the system become very complicated. But one thing to do that, you have a jet engine, aircraft flying air, you have wind turbine connect worldwide, you have a EV network. And last year we produced 6.5 million EV. Is projected by 2025 will be 30 million EV, right? Those will be connected to network during the charging. So during the charging, you have a lot of data as well. Then you have a semiconductor fab. There are 29 fab globally are being built, right? So obviously, during the chip shortage period last few years, Now we have selective growth based on what you're going to make. So, but this connect system, when you're managing, that become very interesting and also complicated. Obviously, there are some uncommon things. For example, each machine working on different kind of working regime, like wind turbine. The wind speed different from mountain to mountain, offshore to offshore, right? Turbine to turbine. You have machine configuration. Your machine build different types, different motor, different gear, different bearings. So different noise level, different environment. And you have a quality, and I mean, some data you have a history, some machine you don't have a history. Some machine are new, brand new. So therefore, you have to collect useful data and useful data. And useful doesn't mean you're useful. So eventually, you have to understand the not just the problem, but also degradation of the system. So today, we'll focus on the variation and also the data usability, because these are the critical thing for a large-scale system. So obviously, you have a usefulness, you have a usability of data. You know, sometimes we have lots of data and we can use it and they're good. Actually, we're lucky. Most of the time, you have useful data, but they're not usable. For example, like you have a fish, it's a great fish, but it came from polluted water, not edible, right? So you donate the blood, your blood has HIV and hepatitis B, then blood is not usable. So eventually, most of the time, we have a useful data, but may not be useful. So we have to try to find those a tiny connection, maybe relate to some potential usage, right? That, of course, you have less useful, then you can weed out. You don't need to continue collecting them. So obviously, this art is a science about how to make data useful and usable. So typically, we build a response surface of a thing, like a measurement, a machine, or a wafer, or a energy profile of a wind turbine, or a EV charging profile. Then, because we know how good it should be, so we can collect high volume, high quality data because we instrument them in the beginning, right? But of course, during the real world, there only may be small areas, small issues that are not perfect. We need to diagnose, we need to predict. In this sense, we only need a small amount of data. We need a high useful data, highly useful data, right? So therefore, you don't need lots of data. So small data, but truly meaningful. So there's a lot of interesting thing. To do this, obviously, we have to develop tools, right? How we make the tool available, and that's able to address these issues. So one thing I like to show all the time is about our perspectives. We divide the space into visible and invisible, and also our strategy is to solve the problem versus to avoid the problems. So you have 4 quadrants, right? Most of the time, we're starting from here. We know what problems are. We've been through the problem for the many years, so we know our lesson. We're trying to avoid that by training people, by using the right tool and right practices. Typically, it's a Lean and Six Sigma process. Eventually, we integrate to the model, the problem that we can do, we can predict, avoid it. But not all sometimes can be transferred, sometimes cannot be transferred because of the parameters, because of inefficient of domain knowledge or different type of a usage. So we need to find out relationship between the known problem and also potential unknown issues, right? For example, machine accuracy could be caused by spindle, by bearing, could be by bore screw, could be caused by thermal distortion, many factors. So when I understand the work environment, understand the type of condition, we probably can correlate that with a thermal degradation based on the machine degradation, based on accuracy drop. Certainly, we want to predict compensation. How we do that, right? Same thing for robots, same thing for wafer yield, right? You have so many wafer sensors in processes. How do you know which sensors are most critical? You have 190 sensors, but sometimes only 25 sensors are most important. So eventually, we need to develop a system, and you can see the blue area is where we see the future AI can help map those needs. Now, of course, in the beginning, we may want to know diagnostics. We want to know how to control them, but eventually we want to know how to predict. That's what the virtual metrology is about in semiconductor. And the manufacturing industry is 4.0 and IoT. And eventually, we want to understand the machine can self-aware as the environment changes. For example, like wind turbine, when humidity is high, temperature is low at night, likelihood you will have ice accumulate on the blade. That will give the more weight on the blade. Eventually, you have less energy power generate. So you have used a cyber environment to understand the changes you can predict, right? So this is what digital twin, not about the machine itself, about machine and those changing environment. How can we create relevant model? Eventually, you can make system worry-free. Before things happen, you can change, compensate, even adjust, avoid. So again, this is something we've been working on, but the challenging thing is that AI is being used for many years, right? It's a cognitive science. It's basically a science-based reasoning about how we model the cognition, perception, right? And also the images in the early years. But more and more so, we use this based on trial and error, try and error. So if you give a same algorithm to two different engineers, same data sets, very often you have two different results. The question will be why? Because each person have different domain knowledge. They will select different features. You give the same fish to chef, two different tastes of a cook. Why? Recipe different, seasoning different, the way you cook food is different. So we cannot do that in engineering system. You have to do exactly consistent way. If there's a crack in the blade, you must have a crack. Doesn't matter what method you detect it, right? So you cannot say, oh, one algorithm say this is crack, another one say likely crack. Then which one should I listen? So therefore, we need a systematic discipline to train engineers to understand how to use a tool the correct way. To do this, obviously, there are many tools over years we've developed, right? So many different tools, but recently a lot of people go deep learning and the KN and the RN. But problem is, how can we compare these tools? Make sure we select the right tools, right? In the kitchen, there are several tools used all the time, every day. Not all the fancy tools, occasionally use it, right? So obviously, so these tools that are there, how do you know which tool is useful? And for example, we can compare the type of a frequent use AI tool, right? Between random forest and logistic regression. If you have a lot of domain background of problem like gearbox and the machine, you can use logistic regression. If you don't, you can use random forest, right? So obviously the tool depends on how you depend on your judgment and how your background and how you select the nature of a tool based on sensitivity, noise level, and also the training speed, etc. So one example, let me show you how we learned a big lesson, right? So in 2005, the Georgetown, Kentucky plant in US, and they had a major shutdown of the machine. Over years, they've have frequent shutdown. So the goal is trying to save 50% downtime by 2008, 3 years period. So one thing is Georgetown, Kentucky is where Camry is born, Camry model is born, right? So today they make not just Camry, but also Lexus and also Prius. So the compressor failure was a big issue. Compressor failed suddenly, and then the shutdown. Then you have a 12 compressor, big facility managing all the important function of a production. So there's often when they shut down, the battery burned out, right? So that's too late. So one thing you could question is why the machine has a shutdown. Why is the machine burned out? It's because of the surge. The surge is behavior of the pressure and also the flow rate of the compression ratio. So you can see the surge line and also your physical operating range have to you have to closer but not too close. And because between efficiency and the risk, you have to judge, right? But of course, when surge occur, and you can see just 1 second and 2 seconds, a machine have a big shakeup. And when the machine starts shaking, then the machine stop damage. That happened only less than 2 seconds. But before that happened, you see about 15 seconds, they have a lot of a transient happening. So now we try to find out what are the parameters. There are 12 parameters like pressure and the humidity and the temperature. So we need to find out when surge happen, if we can detect the surge, can we physically model the control system to let the valve open, can relieve the pressure. If we can relieve the pressure, the surge will never occur, right? That was a good baseline to assume things will work. But the problem is what parameter you need to control. There are 12 different parameters. So first thing we did is we take 12 parameters, we run the principal component analysis, first find out invisible relationships. First, you find out those eigenvalue, the most important, then each important one, you find out those eigenvectors that can be controllable in terms of, like in this case, a position of L and the motor current are controllable. In this case, temperature, yes, but really not up to you. And also there's a humidity. You can just single control, but not a correlated control. So eventually we select the IGV and the motor currents. So based on the two parameters, we can classify how stable the system is, if the between the stable and the surge, what a cutoff line is. So we use a support vector machine learning algorithm to learn the system. Eventually, we can classify them and prevent surge. So since 2005, 2006, there's no single downtime until today. So for almost 16 years, zero downtime. So this article by SME actually interviewed Toyota team, and they learned after 15 years, they believed system can claim zero downtime. Otherwise, you have to continue accumulate enough knowledge. So again, this is an interesting lesson we learned, but obviously the question will be, how do we do it continuously for all the other systems? So 2014, the FANUC also adopted ZDT as a product name of the company called Zero Downtime. So now you can see the company start believing zero downtime is realizable. But back in 2000, and people say, no, Jay, I don't believe you because it's a good dream, but will never happen. But after 15 years, people believed it. So today, we've transferred the algorithms of 15 different algorithms to National Instruments, LabVIEW, so people can start using it, machine learning toolkits. I think the recently math work also start hiring our students, trying to develop similar things in vertical space. So I believe machine learning will become more and more so, become a daily use tool, not just belong to scientists or data scientists, right? So this is one thing we're happy. So let's look at this example. When we have large systems, how do we do it, right? So obviously, when systems are large, then obviously you have to find the purpose. So first example I give to you is during my tenure years in 2019, 2021, and we had a Foxconn create a company called Foxconn Industrial Internet in 2018, right? Based on the change of the world industrial internet. And so at that time, and I served advisor trying to help company connect 175,000 machine tools, 80,000 robots, and 1,800 SMT lines. The SMT is a PC board assembly line, right? Surface mount technology line. So this is a really large scale because, as you know, there's a lot of digital electronics, right? Product made by Foxconn. So obviously that gives a lot of rich data to analyze what's invisible issues behind machining, behind injection molding, and behind a lot of a high-speed assembly system. So this is the baseline system people built. But during the COVID, unfortunately, last 3 years, right? What happened? People could not travel. We could not travel. So we have to support production worldwide, right? So obviously, in this case, if you cannot travel, you have to support production worldwide. What do? That accelerates the digital transformation tremendously, right? So obviously, we start collecting data from different machine, different region, different part of the world. From machine level, like a motor, gear, component. From a different level, you have a injection molding, machining with 175,000 machine tools. Then you have all the correlation of quality. Then you have a production management. Then you have a delivering system. So how you connect things together, and not just a machine connect, but also data collect the right things. But in industry, we call the 3P. You got problems, you have a purpose, you have a process. So data collection is a process, but you deal with a problem, then you solve the problem. How about the purpose? The purpose means really make production worry-free, right? So do this, I remember when I was Japan, 1995, when NSF and sent me to Japan, work in the MITI laboratory. So we developed a first industrial internet-based the remote machine monitoring system. So we're trying to instrument Hitachi Seiki remotely control the machine monitor using cyber physical model. That was the first one actually we announced. And in the real world in 1995, in 1998 paper, we present the first one. But that was based on very limited access of data, right? So we can build we need a model to build it because data is limited. That's why we need a model. But today we have a lot of data. Do you still need a model? Yes, the domain model. So eventually, domain model is different than physical model now, because domain model has a lot of knowledge-based usage. The value is very high, right? So the product itself, the model may be useful, but can be used as reference. So eventually, we connect a beyond just a machine. We have machine, man, material, method, because each one is a representation of quality of a product. So you go to Y1, station Y1, station 1, 2, to YI plus 1. Eventually, we can connect the quality like a river, like a stream. We call it stream of quality, simply called SOQ. SOQ is a traceable systematic methodology for connected quality in a large-scale production system. So by doing that, in 2019, and we instrument in one facility, we got received the 2019 World WEF, World Economic Forum Lighthouse Award. Why? Because we reduced 92% redundant labors. You may ask me, what's redundant labors? Redundant labor means I have to repeat in doing something which is non-value added. For example, I keep watching things. I keep checking on things. Why are you checking? Because you're worried. Why are you checking? Because you're worried. So if I can reduce those checking time, then you're okay. Why? So eventually, that is the one thing we focus on, how to reduce non-value added activities, right? That's 92%, huge number. So eventually, we turn off the lights, right? Lights off. Because when lights off, then you don't have to worry about it. Your cell phone will tell you which machine need to be checked, which parameter need to be adjusted. That's what it is. So we, Vascon, create the number of lights out factory around the world. Eventually, 2022, there are over 100 sites being certified by WEF, and Vascon has 5 sites. Internally, they're building 20 sites as a internal lighthouse to train people and to build a good role model. Again, so this is some good journey and to learn. Of course, when you change that to a different industry like semiconductor, that's a very different animal. Semiconductor scales a lot. You have fabs, $10 billion fab. You have a lot of machines, very expensive, like EUV is over $100 million, right? But the problem is right now for 7 nano, 5 nano. As you can tell. Hello? Yes? As you can tell, based on our journey, as you can tell, based on our journey of semiconductor, this is the journey. This is the history we've been working with a semiconductor. So over the years, from 2000, Intel was our first founding members. So we start working on vacuum pump. Over the years, we looked at metrology and CVD, PVD, and also electrostatic shock for etcher, and eventually moved down to PCVD and also chemical, a material processing CMP, and eventually moved to a 7 nano, 5 nano space. So it takes about 20 years to build such a legacy experience and to move forward. So same thing for semiconductor. We have a visible space. We understand the yield of the wafer, what are quality issues. Then we can understand, categorize them, different clusters. Then we can relate that to certain kind of root causes. Then we can avoid them. But problem is, you have 800 steps, right? So how do you physically manage so many steps? Only about several dozen critical steps. So you need to understand the critical steps. They have different recipes. So we need to understand relationship between the machine and also recipe and how they collaborate. So you can do chamber matching, you can do recipe calibration. Eventually, you can minimize the yield degradation. So again, the blue area again for semiconductor is certainly a systematic way. But today, a lot of practitioners in semiconductor foundry, we're still using design of experiments called DOE. DOE is great, but it's really called try and error, right? So now when you move down to 5 nano space, 3 nano, 1 nano, as we all know, 7 nano is the borderline. We use EUV. 5 nano is most company doing right now, but 3 nano TSMC and Samsung are leading, and 1 nano going to push to the limit. But again, these are the generations we're trying to build, right? So, but typically when you have a semiconductor, you have a typical machine have over 100 sensors, 100 to 200 sensors, and but you have a process control. You can see this the process system based on the sample you collected. You need to understand the knowledge about each process. Then typically, the wafer goes in, then before it goes out, we need to check all the process variations. Then after wafer comes out, we need to check the metrology, make sure they're okay. Eventually, we feedback the loop continuously. But by doing that, it really go a lot of try and error, almost time consuming. But today's modern fab, you have a lot of data, actually. You don't have physically people work inside the fab, but they're more in the data room. There are some people doing the maintenance, but modern fab, lots of data, it's a data-rich environment. So we need a almost real-time computation to analyze this data, right? And to have a quick correction, so you have a high yield throughputs. So if I do that, so one way to do this, like we set a threshold based on the one machine. We measure the golden machine, we identify the major wafer outputs. Then we compare with the target machine, the machine we need to assign. We see how the process can be adjusted differently to get the same wafer, right? But that process is a very challenging, almost you're managing all the wafer line every day. But the uncertainties, different machine, different processes, different yield. But there's lots of variation because the component different, vendor different, the cycle is different. So these parameters are actually constant changes. So it's very hard to have a best optimized maintenance system unless you have a truly control all the relationship clearly. So by doing that, we have deployed called the unique way to understand those important critical steps. So we built the golden machine model based on the matching of the processes. From this, we calibrate the machine based on those critical steps. Then we go to the next target machine, we do the same thing. So eventually, by doing that, you have almost 190 sensors need to be used, but only about some critical step you need to use it. But DOE is very useful, but it limited to the limited parameters. All those knowledge you know well. For those you don't know, your DOE doesn't help you too much. You do try and error. So eventually you can calibrate machine systematically, right? So we can improve the yield systematic way. Why do we need systematic way? Because other people can do the same thing. And sometimes that you can do DOE, but a new person comes in, he or she cannot repeat what you have done. In this case, you have lots of overhead, lots of try and error, which is not systematic. So because time and sensitivity, I cannot go too much, but I like to go to another system. It's called the EV system. EV system is a large scale as well, because so we have a battery, you can machine learn the battery, you can avoid issue the battery usage, but there's a lot of behavior, driver, road condition, traffic, weather, those are invisible parameters. Those you cannot see those, but they happen constantly. So eventually, you want to model the battery based on worry-free driving, because I can know exactly how's my battery degradation based on the usage, weather, and also traffic. Today, you just look at the mileage keep going down. You don't know why, right? So one thing to do that, to first understand invisible battery charging, discharging. So by doing this behavior, you can categorize which one is truly usable and which one degraded and which one is unusable. So that's a very fundamental data issue of a battery, right? Like I said earlier. So this is a very critical step to have such kind of understanding of a domain knowledge. Then, of course, you can start instrument those battery usage and the battery impedance parameters, and you have a stable charge and stable health. So these things you can model that based on different type of battery, but same method, right? So over years, we built such a methodology can duplicate. For example, you're driving economically, I can see the current voltage temperature changes. If you aggressively, I can see a different number. So this, by doing that, I know exactly how aggressive you are, right? Based on, so that's why if you own a Tesla, right? Tesla have a insurance, like I own Tesla Model Y. Every day, my wife tell me, Jay, you have a too hard stop, top brake. You have a hard brake. You have you cut short too tight, and you follow car too close. So she know how I drive, right? Of course, if you drive good, the Tesla give you a $5, $10 discount next month. That's called the insurance, right? Evidence-based driving insurance. But again, Tesla hired 3 of my PhD students. Certainly, they are interested in such things. Now, we can either look at those at cell level. Cell level mean each battery cell is different. Because you have over 4,000 cells, which cell degrade the most. So during the recycle or reuse, you know what to replace rather to replace everything. So again, these kind of things that you need a good knowledge domain and data. So simply speaking, currently we're working on the OTA, over the air. So 2012, before Tesla started, we instrument the OTA, actually over the air, and software, how to use that to managing the battery, right? So that set a very good foundation of today's OTA cloud-based system. You can download the tool, you can do autonomous driving right away. You don't have to own it. You can just use it, pay by month for the autonomous driving. So now we are building a virtual battery, right? Virtual battery means today, Tesla battery, you manage Tesla. You have a other company, you can manage their own battery, but they are not shared. The virtual battery system you can share. It doesn't matter which battery. I can use the same model to use for your battery as well. See, that is the first time people can do, right? So eventually, that's one of the things we're trying to develop. So in the real world, you may ask me, why it matters? Well, it's not just battery, it's about how we use a tool to integrate all the vehicle sensors. Vehicle has over 150 sensors in the EV, right? iPhone has about 1,000 sensors. Vehicle has about 10,000 sensors. The sensors, but when you correlate with a GPS locations, you can predict what's going on the road. For example, there's a barrier, there's a big potholes on the road. The car sensor, you can label the next car, and you know, oh, 1 kilometer ahead, there's a pothole. For example, you drive the car, right? Sorry. You drive a car, you hit a pothole. The pothole happened, I label the pothole locations. I share the same kind of a social network. The other car will know there's a pothole 1 kilometer ahead, right? Now, of course, you drive in some, eventually those things currently is not on the traditional social network like Google Map and whatever. So eventually the sensor become a good labeling system. And with the LEO, low Earth orbit, LEO and the system connect to the cell phone, connect to the vehicle, that will make the future data-centric systems more interesting. So finally, conclusion, because time, I want to say that today, because we talk about AI for everybody understanding, AI is happening in our industrial system, in manufacturing, in our GV, in our semiconductor, in our almost day-to-day. So to do this, one thing we need to understand, data science is really about data science, right? About data. A lot of AI people belong to that field. But problem is, if you look engineering, we have semiconductor, we have healthcare, we have energy, we have smart manufacturing, we have so PHM, prognostic health management, is a field that connect between data science, right, and the domain. So industrial AI is the discipline, how we train people systematically. So you are not the one solve a problem only by you. Other people can repeat your success, even to accelerate, to transform better. So this is a very important industrial AI system. It's not by data scientists only, right? By all engineers in all kinds. So to do this, of course, it takes time, but we believe we are confident that one day we'll have good engineers, many good engineers can do the things successfully and sustainably. So this book we published 2 years ago, called Industrial AI by Springer. And this course, I've been teaching this course for many years. We believe that the time is ready for many engineers to learn more things. Again, thanks for taking time to listen. I hope that I present is some good reference for you to think about. Thank you.
Thank you, Jay. This is a very impressive talk. I've known Professor Li for nearly 20 years. I know his work and I follow his work very well. And Jay is an eminent scholar in predictive maintenance with a very strong track record in academia, but also have quite a lot of extensive industrial experience. As you've seen from the case studies, success stories based on real-world examples. So today really is an opportunity for the online audience to spend a minute or two to raise questions. This is opportunity for you to discuss and find out more through this platform. While you are casting your questions, perhaps I can ask first the question. Jerry, you mentioned that you are using this data-centric approach. Of course, it's AI-driven. Combine AI algorithm with a data-driven approach, try to find out the value of data. There's one issue that people doing big data-related research is veracity or reliability of the data, trustworthiness of the data. If someone hacked the sensor or the sensor controller, try to send out wrong information to misleading you, that could be a big problem. It could be false positive, so you base it on wrong information, make a decision, make system or machine burn, or false negative, and you also encounter another problem. How is your advice or approach to deal with this problem?
I think this question you ask is a very critical, very important, because one thing we look at the complexity, and the second thing we look at the security, and thirdly we look at the resilience. So when sensor behavior changes, right, and could be intentionally, could be naturally. Naturally means sensor degrade. Intentionally, there could be offset by some situation. The system, normally what we do, we have called a pattern behavior. So we know the environment changes, then we can predict what sensor routine should be. Now, when the environment changes, when the environment doesn't change, the sensor behavior changes a lot. Something's wrong, right? So like a wind turbine, you have a low humidity and a low temperature, high humidity. Likelihood you have ice accumulate, right? You have very high temperature, you have a low humidity, you don't have ice, right? So obviously, so the system can judge. And by doing that, we can do first layer of a data quality evaluation. Second layer will be before the sensor go to the human, we really tell you this is an outlier or the special case. Human being can also use domain knowledge to make another judgment. This is a machine I just maintained, and maybe some wrong. Let me check. So, or machine has been maintained very high quality. It cannot be that way. So first layer is machine level. We do self-assessment. Second level, human level. Then third level is you can make decision. So you always have a buffer to make things become more resilient. Yeah.
Mm-hmm. Yeah, you also mentioned the transparency of the data, but at the same time, there's a privacy issue, especially for industrial system. If something very useful from academic perspective, it's better to use a transfer learning approach applied to another industry. But in the practical industrial world, it doesn't work that way. How to make use of a data transparency, algorithm transparency, at the same time protect the privacy of business owner? That seems to be another challenge.
Yeah, I think privacy, security, I think that they connect together, right? Privacy about who should see, who should not see, right? And that's very important. And also the security about where to go and where should not go. So once for people, once for the system. So basically, what normally we do is we use a federated learning. So basically, we correlate those relationships and to into one correlate a label like blockchain. So that data for this piece have to go where, and this data code that piece can go where. For example, let me give an example. I have a machine producing wafers, and one's for high-end chips, one for just a high volume consumer chips, right? So when I see recipe A, I know this is for high volume. For recipe B, that's for low volume but high sensitivity. So I know certain kind of parameters. I can categorize. I know where chip should go. Now who should use information from category A, category B. So by doing that, then I know how to assign to different people, different machine, different shift, and different tracing system. So again, so federated learning is transfer learning is very good, but there's a one limitation because sometimes machine is built by different generations, right? This is newly built. Your old machine, different spindle, different bearing. So we tried transfer learning, didn't work. So we have to make offset program. First, run machine idle. During machine idle, I know exactly how consistent machine behaviors are. Then we can readjust the parameters, make the model fit that machine. But that takes time. So, but again, there are different methods, but important things managing who should see it, who should not see, and what data should go, what data should not go. So by understanding the pathway of data, I think we can easily select the best tool managing the security and also transparency of data.
Thank you, very good. Now we have one online question, and Jay, you can also check your chat box. I can read it for everyone. Thank you, Professor Li. I observed you don't have any partnership with the companies in Africa. Is it possible for consideration of startup companies requiring industrial AI? This question is from Collins Akumabo.
Yeah, there are lots of data availability right now in open source. For example, if you look at the data challenging for PHM Society, PHM, Prognostics and Health Management Society, PHM, and every year they have open data sets, and this year is rock drilling data. Since 2008, they every year have different data sets. 2008 was a jet engine data. 2009 was a gearbox data. 2010 is a CNC machine data. 2011, I think, is wind turbine sensor data. So each year, different data sets. So for those people who have no domain knowledge or domain data, you can repeat what people have done to compare how much you can do better, because they have done it, so you can compare the baseline, the ground truth. So of course, there are also other open source data by different kind, like Bosch has a lot of open data sets. Fastcon also a lot of data set, open data, open source. So to me, I have about over 30 different open data sets we use to train students, and from gearbox, wind turbine, jet engine, semiconductor, battery, healthcare. So I think that would give students very good experience to deal with different type of domain data sets. Yeah, and I think they can Google PHM Society. They can find lots of data out there.
Yeah. I hope this answered your question, Collins. Otherwise, you can raise a follow-up question. I can follow up with another question. Professor Li, you focus quite a lot on predictive maintenance. Prediction is important to look into futures. In a dynamic environment, the situation change. If we look too much into the future, the reliability decrease. So what would be this, what is a suitable time frame that you consider is a reliable, practical for prediction?
I think there's two different way to do it, right? I understand the question is interesting, and also is a kind of depend on what application you're talking about. Number one is a single machine based. Number two is a fleet based. For example, if I only monitor a single machine, like one jet engine, just one, well, the machine has to be physically in the usage. So once you start connecting airplane, driving different altitude, different airport, different weather, the data change dynamically, right? So, but you have the purpose, like I said, the purpose that what are you monitoring? Are you monitoring the safety? Are you monitoring the efficiency? Are you monitoring the, whatever, right? So I think the first purpose, what do you want to do, the purpose? So when you have a large number of a system, for example, you have a 1,000 robots in the factory. Are you going to monitor every robots? Probably not. It's not practical. Too expensive, right? You need a lot of AI engineers in the factory. No, you should be focused on making good cars. So therefore, what people do is using similarity based. I can compare similar operation quickly to understand which machine. We rank all the machine every day. So we only focus on the low performance bottom 5%, right? So you don't have to monitor all the machines. You focus on those low performing machines. So therefore, to answer the question, if you only deal with one machine, you have to understand all the dynamic working regimes in order to know whether reliability makes sense. For example, I'm an airport, very short runway. My airplane take off very quickly, like a Reagan National Airport in Washington, D.C. The jet engine pressure and combustion is very high, right? So if you think something wrong, well, it take off, right? Take off. But if you're a different airport, they take off very smoothly. They don't have a kind of an issue. So you got to know the domain knowledge before you judge something wrong, right? Yeah. But when you have a lot of numbers, for example, 2 engines, I can compare 2 engines to see which engine is good. You got a fleet of engines, right? You got all the today you got 100 engines, 100 airplane. I know 200 engines. I can compare which engine is the worst. Yeah. So again, there's a lot of way to do it before we zoom into just one specific problems.
Mm-hmm. Yeah, consider the fleet information.
Yeah.
Use a big data approach.
Exactly.
Now we have another question from Jin Cui. He said, "Thank you, Professor Li. What do you think of the balance between data pre-processing techniques and complex machine learning algorithm, like the Toyota example? The PCA method is used to select the key parameters, and SVM is employed for classification. Thanks."
Yeah, I think this question is very good. I think the several things, right? So normally in the beginning, we don't understand, for example, that example of when the customer came to me with a bearing problems, actually misled us to look at bearing problems. Bearing is not a problem, right? So like, oh, you have a heart pain. Heart is not a problem. Probably is depend on your food, you eat, the drink, right? The smoke. So the reason, so heart is a symptom, but real cause of the bearing damage is what the reason. So what I'm saying that sometimes the problems may not directly tell you the parameter you should collect. So we made a mistake at that Toyota example. We went ahead to collecting vibration data of a bearing. Actually, first 6 months we failed. Actually, though I did not tell about our story. We failed the first 6 months because we went to monitor the bearing vibration. We missed the opportunity to monitor the search because you told me a bearing problem, right? So it's wrong because bearing failed very quickly. Even you can detect vibration too late anyway, right? So that was a wrong approach. So when customer bring you a problem, remember that may not be the real problem. Like I said, invisible. The invisible will be something else. So we need to start understanding that something else, like what condition you're talking about. That's why doctor always, you have a headache. Why? Do you smoke? No. Do you have good sleep? No. Do you have a lot of stress? No. Oh, what condition is right? Oh, when I have a sun glass. Oh, okay. Maybe your visual cause a headache, some nervous system. So again, there are a lot of things doctor have to find out, eventually they have to do a brain MRI to find out why headache, right? Get invisible data out of it. So again, PCA is to find out invisible relationship. But once I know the relationship, support vector machine is easy to choose, right? Either I can use a support vector machine for supervised learning, or I can select the k-means, right? Or I can use a self-organized map, minimize quantization error. I can do the same thing. It doesn't matter SVM only, right? So once you understand the background, there are many tools you can use. Yeah.
Thank you. I do not see further questions from online audience. For the future, this predictive maintenance business, and your aim for the purpose is worry-free. Over time, new worry may be developed. How the system can learn to maintain this worry-free dream forever. What's your approach to deal with this dynamic world?
Yeah, I think this question is good because the reason I call the purpose is that, right? The purpose may change. For example, you have like a world-class companies. Now people want to carbon neutral. You have a world-class quality. Okay, but I want a quality. Also, I want a carbon neutral. Okay, I got a headache now. High quality carbon neutral production. Okay, I need to find out how to achieve carbon neutral. First, find out how we generate the different carbon dioxide in each process, and how we understand the electrical usage, the power usage, and how we look at the chiller, which is the biggest item in the foundry or in the SMT line, create chillers, a lot of the electricity used, right? So we categorize priority and the Pareto chart. So again, so yes, you're right. The worry always add on based on how good you are, right? So you're rich. Once you become rich, you have to have a good taste. You have a good taste. You have good knowledge. So you stop challenge yourself to learn more things, not just become rich man only, right? So again, worry is just about how we elevate ourselves to a level, not just to make what we know well, but also how to make society better, how to make something we don't know well, right? So how, for example, manufacturing company, how do you recruit young people come to work? That's worry. Today, you cannot find enough workforce, right? And you give a lot of pay, people still not come. Why? Because they don't believe, and manufacturing is what their interesting job. So why? Because we are not making that interesting job. We need to make commitment to make manufacturing a noble profession to attract young people, right? So again, so there are many things we have to define what worries are. But again, come down to it, we have to start think ahead. Manufacturing is really about a noble profession, so we have to invest to make that field more exciting, not just a more intelligent, right? More intelligent and more exciting, so people can join the workforce. They can collaboratively make a good legacy, right? So not just for societal point of view, and also from the technological point of view. Yeah.
Thank you. I think this is a good summary of your own keynote talk today. Thank you very much.
Thank you.
Yeah. And for the next webinar, it will be on December 9th. So for online audience, I look forward to welcoming you back to this webinar series, AI for Manufacturing. Thank you, Jay. Thank you again.
Thank you.
Bye-bye.
Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build a program. Let's shape the future of AI for Good.